In Lesson 5, our basic proof rules were already enough to prove any valid argument to be valid. But by adding a few additional rules for some common proof steps, we'll actually be able to simplify the proof process a little bit. So we're going to look at 5 additional proof rules in the natural deduction system, and we'll look at the schematic and then how to apply them to some lines of the proof. Note that in Chapter 20 of the textbook, you can find the proofs that each of these rules, and actually a few from the last lesson too, can all be derived from other rules. So each of the rules we're going to look at now is a shorthand for part of a longer proof using our original rules. The benefit of adding these additional proof rules is that they'll just make our lives a little bit simpler. The first rule we're going to look at, disjunctive syllogism, allows us to prove one of the disjuncts of a disjunction without always having to use 2 subproofs as is required by the disjunction elimination rule. So normally when we see a disjunction, the only way to use the sentences that combine it is with the 2 subproofs of disjunction elimination. But with this rule, if we have a disjunction plus the negation of one of the disjuncts, we then get to add the other disjunct. On the left, we have the schematic with the basic structure of the rule. Reminder, A and B are our metavariables for any sentence of truth functional logic, and M and N are our line number variables. So imagine we have a sentence A or B on line M, and then the negation of one disjunct B on line N. We can add the other disjunct on a new line of the proof. So here we add A. And if we have A or B and the negation of the other disjunct, so we have not A, we can add B to a new line of the proof. And this is justified by disjunctive syllogism and the line on which the disjunction appears, M, and the line on which the negated disjunct appears, N. We've got our example to the right with part of a proof, and we see it starting at line 4 with the disjunction. Line 7 has the negation of the first disjunct, not R. Since we have a disjunction, not R or T, and the negation of that first disjunct at line 7, we can add the other disjunct T on a new line, here line 8. And that's justified by disjunctive syllogism lines 4 and 7. Notice that what appears on line 7 is exactly the negation of one of the disjuncts. So in that case, since the first junct was already a negated sentence, we needed line 7 to have a double negation. It needed to be the negation of not R. The idea behind this rule is pretty simple. Think about it this way. If we can prove a disjunction from one of our assumptions, we know that that disjunction would be true whenever at least one of the disjuncts is true. If we find out one of the disjuncts is false, that's when its negation appears in the proof. The only way for the whole disjunction to be true would be if the other disjunct is true. Our next rule, modus tollens, allows us to shorten one of our additional inferences from a conditional statement. So the rule works this way. If you see a conditional on a line of a proof and the negation of its consequent on another line, you can add the negation of the antecedent to a new line of the proof. In the schematic, we have the conditional if A then B on line M, and the negation of the consequent not B on line N. And that allows us to add the negation of the antecedent not A on a new line, justified by modus tollens and the lines on which the conditional and the negation of the consequent appeared, M and N. And here's our example. We have if not R then T on line 6, and then at line 8 we have the negation of the consequent, not T. Then we add the negation of whatever sentence is in the antecedent. So since the antecedent was not R, we need to add the negation of not R, or not R, to line 9. And that's justified by modus tollens applied to lines 6 and 8. For this rule, the idea is that if we can prove a conditional, we're assuming it to be true. If we know the conditional is true, and then we find out the consequent is false, the only way for a conditional to be true if the consequent is false is for the antecedent to be false. Seeing the connections between our truth tables and our proof rules can sometimes help you grasp the intuitiveness of some of these rules. In our examples in our last two rules, we introduced double negations. And now we're going to introduce a rule for eliminating double negations. So if we have a doubly negated sentence on one line, we can add the sentence itself on the next line, or any subsequent line. So if you have not A on line M, you can drop the double negation to get A on some subsequent line and justify it with double negation elimination and line M where the double negation appeared. And our example illustrates that A can be a sentence of any level of complexity. So here we have the double negation of not Q if and only if not R on line 8. And then the double negation elimination rule allows us to drop the two negations and just get not Q if and only if R on line 10. And that's justified by double negation elimination and line 8 where the double negation appeared. It's important when using this rule to be careful about the scope of negation. So on line 8 there, the first two negations take scope over the whole biconditional. That allows us to apply this rule. The third negation there, right to the left of Q, takes scope within the biconditional. That is, it's part of one side of the biconditional. Parentheses are super helpful here for monitoring the scope of negation. And to get a feel for how this rule works, think of an example of a doubly negated sentence of English, like, the offer is not unreasonable. That sentence roughly means that the offer is reasonable, and so the double negation rule seems to capture how we often reason in ordinary circumstances. Our next rule, excluded middle, is the only one of our new rules that will require subproofs. The way this one works is that if we can prove some sentence by assuming another sentence and its negation in two separate subproofs, we can add the first sentence to our proof. So more concretely, let's look at the schematic. We've got two subproofs, one that runs from lines I to J and the other that runs from lines K to L. The first one introduces A as its assumption, and the second introduces not A as its assumption. So we have a sentence and its negation as our two assumptions for excluded middle. And our goal is to prove the same sentence B from both of those assumptions. If that's the case, then we can add B outside of those subproofs and justify it by excluded middle on lines I to J and K to L. And to the right, we have the rule in use. So let's say we're looking at line 8 of some proof. So we see our two subproofs starting at lines 8 and 10. One starts by assuming P, the other by assuming not P. And both of those assumptions allow us to prove P or not P, in both cases justified by disjunction introduction. Since we can prove P or not P from both of those assumptions, we can add P or not P to our proof at line 12. The idea behind this rule is that if some sentence follows, regardless of the truth of some assumption, that sentence ought to also be true. The final rule we're going to look at is actually a set of 4 rules, and they capture 4 provable equivalencies between sentences involving negation, disjunction, and conjunction. We've actually already talked about De Morgan's rules before in lesson 2.3. So you might remember those sentences about Shelley not eating peas and or carrots. Those were all illustrations of these rules. So on the left-hand side, the rules here capture that Shelley didn't eat the peas and the carrots means the same thing as Shelley didn't eat the peas or didn't eat the carrots. And the right-hand side captures that Shelley didn't eat the peas or the carrots means the same as Shelley didn't eat the peas and didn't eat the carrots. So looking at the schematics, the left-hand rules show that the disjunction of 2 negations, not A or not B, can be inferred from the negation of a conjunction. It's not the case that A and B, and vice versa. The right-hand side shows that the conjunction of 2 negations, not A and not B, can be proved from the negation of a disjunction on line M. It's not the case that A or B. And also the reverse below. The trickiest thing about the De Morgan's rules is that it can be a bit hard to keep track of the scope of negation. So we'll illustrate one of the 4 versions of this rule, and we'll look at a pretty complex example to show how you have to be mindful of negation. I've copied this schematic, so we're looking at the one where we have the negation of a conjunction and we prove the disjunction of 2 negations. And that's illustrated with these lines 4 and 5 of this hypothetical proof. So the first sentence is a negation of a conjunction with not G as one conjunct. So that takes the place of A in our schematic. And F if and only if E as the other conjunct, taking the place of B in the schematic. By correctly applying De Morgan's rules, we get a disjunction with the double negation of G as one disjunct. So that's our double negation of G is our not A. And then we have the negation of F if and only if E as our other disjunct. So the negation of F if and only if E is our not B from the schematic. Note that if we see not G on its own later in the tree, we can drop that double negation. But the De Morgan's rule on its own does not allow us to do so. So we have to maintain all of these negations according to this rule. And with that, you now have 5 additional rules to use, which are shorthand for some common proof steps and will substantially shorten our proofs. So we could do without them, but they'll make our lives easier.